Agilent's Electronic Measurement Group. I'm Don Toot, editor of Electronic Design. Some words about today's viewing experience. First, if you have any technical difficulties during the session today, the first thing to try is function key F5 on your keyboard. That will refresh your webcast console. If you need further assistance, click on the yellow help icon below the slides. To maximize the slide presentation window, press the small green button at the top right corner. We welcome your questions during today's event. Type them into the question window on the side of your screen and hit submit. We'll answer as many as possible during the Q&A that will follow the main presentation, but there's no need to wait until then. Feel free to send in those questions at any time. Today's session is being recorded. It will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides today by clicking the green folder icon in the toolbar beneath the slides. Now let me introduce today's speaker. Dr. Jian Yang is R&D engineer for high-speed digital signal integrity simulation with Keysight ease of EDA. His past experience includes 10 years as R&D engineer, 10 more years as R&D manager, and 2 years as a field applications manager. He earned his PhD in electrical engineering from the University of Electronics, Science and Technology in China and held postdoctoral fellowships at the University of Waterloo before joining Keysight ease of EDA in 1992. And so let me turn things right over to him. Jen, the floor is yours.
Thank you, Don. Hello, my name is Jian Yang. I'm an R&D engineer at Keysight ease of EDA. Don was saying ease of EDA is EESOF. My colleague Colin Warwick will be available at the end of the webcast to answer questions. Keysight was formerly known as Agilent Electronic Measurement Group. In November of 2014, Keysight was spun off from Agilent, and it became an independent company. It has 9,500 employees, and we are serving customers in over 100 countries. Here is today's agenda. I will first introduce USB 3.1 physical layer, or PHY. I'll review USB 3.1 compliance test from a measurement point of view. I'll then discuss USB 3.1 PHY simulation to compliance test. At the end, I'll summarize and answer questions you may have. USB is the most successful interface in the history of PC. The adoption is virtually 100% in PC. Many peripheral devices, such as thumb drives, removable disks, printers, cameras, adopted the USB interface as well. The adoption is still growing at a rate of 3 billion units per year, especially in mobile phones and tablet computers. USB 1.0 was introduced in mid-90s, and USB 2.0 was a quantum jump in transfer speed, as shown in the table to the right of the graph. USB 3.0 was yet another quantum jump in transfer speed. We are at USB 3.1 release right now, which has a transfer speed of 10 gigabits per second. While in layman's term, a full-feature HD movie can be transferred over USB 3.1 cable in about half a minute. Well, this is the USB evolution history. USB 2.0 was introduced in 2000. That was 15 years ago. It has 4 signals, that is D plus D minus, and V bus, that's the power, and ground. USB 3.0 was introduced in 2008. It added 4 additional signals, so that makes it a total of 8 pins. USB 3.0 was introduced. USB 3.1 was introduced in 2013. While the pins are the same as 3.0, and it has a couple of physical layer changes and protocol layer changes to support 10 gigabits per second. It is backward compatible with 3.0 and 3.1. I'll use this diagram to introduce the USB 3.1 terminology. Conceptually, USB specification follows the OSI, or Open System Interconnect model. It is partitioned into several abstraction layers, as shown on the left-hand side of the diagram. The physical layer at the bottom, the link layer is above the physical layer, and the protocol layer and the device host application layer is above the protocol layer. USB 3.1 supports 2 speeds, that is Gen 1 speed at 5 gigabits per second, and Gen 2 speed at 10 gigabits per second. Here's some more terminology I'll use in this webcast. So USB 3.1 Gen 1 is sometimes referred to as USB 3.0 or SuperSpeed, running at 5 gig per second. USB 3.1 Gen 2 is sometimes referred to as SuperSpeed Plus, running at 10 gig per second. Compliance, that's the word I use often in this webcast. Compliance refers to adherence to standards in order to achieve interoperability. The other 2 words, normative and informative, those words are used in the specification. Normative refers to required. Informative refers to recommended rules in the standards. The words host, device, and hub refers to computer host, peripheral device, and connection hub. PHY refers to physical layer. Physical layer includes the electrical transmitter, the receiver, put together also known as the transceiver. And then when we talk about the PHY, the electrical transmission medium, such as cables, connectors, PCB traces, and IC packages, are all part of the discussion. Then there are a couple of abbreviations like CTLE, DFE, CDR. They stand for Continuous Time Linear Equalizer, Decision Feedback Equalizer, and Clock Data Recovery. They are the signal conditioning and the data extraction circuitry inside the receiver. Then pre-emphasis, pre-shoot, and de-emphasis, they refer to electrical signal conditioning inside the transmitter. So I'll use these words in the webcast. Hopefully you either keep this in mind or reference these words if you get lost when I go through the presentation. This is a quick comparison of Gen 1 and Gen 2 PHY layer. So of course the data rate, Gen 1 is 5 gig, Gen 2 is 10 gig. The encoding scheme is changed from Gen 1 to Gen 2. Gen 1 is 8-bit / 10-bit. That is, for every 8-bit of data, there are 2 bits overhead added. That's like a 20% overhead. where in Gen 2, the overhead is reduced. For every 120 bits data, there are 4 bits overhead added. The reference equalizer in the transmitter is changed. In Gen 1, only the de-emphasis was required. In Gen 2, both de-emphasis and pre-shoot are required. And the reference equalizer inside the receiver is also changed from Gen 1 to Gen 2. In Gen 1, only CTLE was required. In Gen 2, both the CTLE and a one-tap DFE is required. The clock data recovery from Gen 1 to Gen 2 also has a change. That's the jitter transfer function bandwidth is changed from about 5 megahertz to 7.5 megahertz. The eye height and eye width or eye mask is even tighter in Gen 2. And the total jitter requirement is also tighter in Gen 2. The target channel loss is different from Gen 1 to Gen 2. I won't go into too many details of the transmitter equalization. So this is the transmitter waveform. Basically, it has several definitions. Well, like the pre-shoot definition, the de-emphasis definition, and so I won't go into too many details. Let's move to the next slide. This is the Gen 2 reference receiver equalization. Again, there is a engineering change notification in last September. Now the AC gain is 3 dB, and there are 7 different levels of DC gain. And following the CTLE, there is a one-tap DFE. So this is the receiver equalization. On the right-hand side, you see several eye diagrams. So the eye at the end of the channel is pretty much closed. Then after CTLE, you see some opening, and the DFE will open the eye even further. This is the USB 3.1 Gen 2 reference channel, and basically it has the reference host on the left-hand side, reference device on the right-hand side, and the cable assembly in the middle. There is a short channel. There's a long channel. The short channel typically has no cable involved. It's just like a connector connecting the host to the device, or there's a short cable, where the long channel has much more loss. Actually, in the middle, I said it's a 3-meter cable. Actually, that's a typo. Yeah, for USB 3.1, it's typically less than 1 meter cable length. The host side has much longer PCB traces, and the device side has longer PCB traces as well. This is the USB 3.1 channel budget. I put the Gen 2 numbers in this red box. One thing you notice is the loss budget on the host side and the loss budget on the device side are symmetrical. And the total loss budget is 23 dB. USB 3.1 introduced a new type of connector called a Type-C connector. And this was introduced in August of 2014. So this was published concurrently with power delivery tool specifications. This is a lower profile connector, and is reversible. That is, you don't have to look at which way to plug in anymore. Either way, will work when you plug this connector to a receptacle. And it has 24 pins. So if you remember previously, the USB connector had 8 pins. Now each side has 12 pins. And it has the power delivery capability. And it has alternate modes. What that means is when the USB communication partners are identified, the communication could happen in other protocols. For example, the DisplayPort or even Thunderbolt protocols. So that's a new connector type for USB 3.1. So that's a quick review of what USB 3.1 is all about. And next, I'm going to give you a very brief review of USB 3.1 physical layer compliance test from a measurement point of view. Keysight had webcast in those areas. Like yesterday, there was a webcast mostly focusing on the transmitter test. And earlier in March, I believe, March 11th, there was a webcast focusing on USB 3.1 receiver compliance test. And last year, I believe last August, around that time frame, there was a 3.1 interconnect test focus. So although the USB 3.1 specification was published a while ago, the compliance test specifications are not published yet. They're still work in progress. So for transmitter test, is mostly focusing on the transmitter eye test, and there are specifications on spread spectrum clock profile test and a low frequency periodic signaling test. For receiver, it's mostly a receiver jitter tolerance test. And basically, after the channel is calibrated, then you change the sinusoidal jitter amplitude and the frequency and do the DER test. For channel, it's fundamentally an S parameter test. Then from S parameters, the channel matrix, such as insertion loss fit at the nyquist frequency and others, can be derived. So these compliance test specifications are still work in progress, and they won't be published the estimate is that won't be published until the second half of the year. Keysight has a comprehensive set of tools to simulate USB 3.1 designs and test USB 3.1 prototype hardware. So on the left-hand side is the design and the simulation software. That's the Advanced Design System or ADS software and EM Pro software. And on the right-hand side, you see 3 columns listing tools for transmitter test, for interconnect test, and for receiver test, respectively. For USB 3.1 transmitter test, the instrument is an oscilloscope, typically with 16 gigahertz bandwidth or above. If you want to ask why 16 gigahertz, so the fundamental frequency of the 3.1 is 5 gigahertz, and to get good edges, you need 3 times of the fundamental frequency. That's 15 gigahertz. You give yourself a little room, so 16 gigahertz oscilloscope will give you valid measurements. And the compliance test points are at the SMA connectors, as shown on the right-hand side. Those little round shapes, they're SMA connectors. I'll say a few words about the compliance test channel. There is a host compliance test channel. So if the DUT or device under test is a computer host, you would use a host compliance test channel. There is a device compliance test channel. So if the device under test or DOT is a device, you use that device compliance test channel. So when we talk about the S parameters or 4-port S parameters or S4P for a compliance test channel, it is actually 1/2 of the full link. Only when the DOT channel and the compliance channel are put together in actual test, we have a full link. So I feel like it's worthwhile to clarify what a compliance test channel is. So here is a screenshot of the USB 3.1 test compliance compliance test software, and actually it is representing a test measurement vendor's method of implementation based on the compliance test specification. So of course this is a Keysight method of implementation. Other companies have their own, and this compliance test software typically runs on an oscilloscope, and the Keysight compliance test software runs on the Keysight oscilloscope. It also runs on a standalone laptop PC or desktop PC. Switching gear to the receiver compliance test, the instruments involved in a receiver test are typically a pattern generator and an error detector. That is the kind of like the box sitting underneath the laptop computer. Actually, that box is called BERT, or bit error rate tester. It has the pattern generator. It also has the error detector inside. Then there is the oscilloscope involved. That is the box on the left-hand side, and the oscilloscope is mostly used for calibrating the measurement. And the compliance software runs on a laptop computer sitting on top of that BR tester. And on the right-hand side is a kind of like a test fixture with a DOT hooked into it, and you see the pattern generator, the two cables on the left, stimulating the DOT, and then there's a loop back path. Those are two cables on the right-hand side going back to the test instrument for error detection. For a receiver compliance test, there is a fairly sophisticated calibration procedure, but after all the calibration is done, what's going to happen is the jitter tolerance ability of the receiver will be tested by changing the injected sinusoidal jitter frequency and amplitude. And the compliance test spec specifies a set of values listed in this table. So at each SGA amplitude and frequency, there will be a test run, and there will be a bit error checked. And for 10 billion bits, 0 error or 1 error is a pass. If there's more than 1 error, it's a fail. So that's what a receiver compliance test is all about. This slide is about the interconnect test or channel compliance test. So the instrument involved in this test is a vector network analyzer, and there are test fixtures, and you connect your cable connector assembly to the test fixture, and there is a calibration procedure to get clean S parameters. Then the channel matrix can be derived from the measured S parameters. And typically for interconnect, the attenuation, the channel attenuation, the reflection, and crosstalk are the three main signal integrity impairments. And then there are three channel matrix. One is insertion loss fit at the Nyquist frequency. The other one is integrated multi-reflection, or IMR. There's a third one called integrated crosstalk, or IXT. So three channel matrix can be derived from the S parameters measured with a vector network analyzer. So now I'm going to switch gear to the physical layer simulation to compliance test. So this is a high-level diagram of the full link channel. So the host is on the left, the device is on the right, and the cable and the connector are in between. And on the host side, the transmitter, the receiver, or the transceiver are on the chip, and then the signals will go through the chip package and the PCB traces and via transitions. And then on the device side, the reverse is also true. That is, the signal goes through the device side PCB traces and via transitions, come to the device side IC package, and arriving at the IC pad. The models used in such a link simulation are the transceiver models. They can either be IBIS or IBIS-AMI models, or they can also be SPICE models. Typically, they are like encrypted in order to protect the IP. The PCB traces, the vias, and the cables and connectors are typically represented by S parameter models. Sometimes the packages or the vias can also be represented by lumped circuits, depending on what simulator you use and what models you get from the vendor. Those models can be mixed and matched in an overall simulation. So the intent of the compliance test bench is stated on this slide. So let's say if you are a designer on the host side, you can swap out the simulated test bench's generic transmitter, receiver, and host PCB model with your actual measurement models or your validated models. If you are a designer on the device side, you can swap out the generic transceiver models with your validated device transceiver models or package PCB models. If you are doing cable assembly or interconnect designs, you can swap out the actual the simulated test bench's reference models with your own or with your actual measured S parameters. Then you can run a sign-off compliance test on the simulation test bench waveform before committing to any hardware fabrication. And the compliance tests you run with the simulation waveforms will be the same exact tests as the ones running on the scope. So that's the intent of the compliance test bench. So the overall flow of the compliance test bench is going to be described in the next couple of slides. So first of all, you can set up a overall link level simulation. So on the left-hand side is a transceiver model. Then the PCB, the host side PCB models are modeled as transmission lines. Of course, the via transitions can also be added as black box, as parameter blocks or lumped circuits. Then the cable and the connector models, you can use the reference models or you use your own models. Then the device side is similar. That is, the transceivers are encrypted HSPICE models or IBIS-AMI models, and the PCB and the via transitions are S parameters or transmission lines. So you run the overall simulation. You can look at the eye diagram at different probing points. And at the end of the simulation, the waveforms are saved into files. So on the right-hand side, you see the variable block and the measurement equation block. Those are the equations to save the simulation waveforms into files. Once the simulation waveforms are saved, then you can start the Infinium offline software, which runs on the PC. By the way, the Infinium offline software looks exactly the same as the software on the oscilloscope. It just runs on the standalone PC. So you can invoke the USB 3.1 compliance test application, which looks like the screenshot here. Now, typically, the waveforms come from the actual capture in the measurement setup. But here, in the circle, you see there is another way of getting the waveform, that is, using the saved waveform. And in this case, the saved waveform comes from simulation instead of from a measurement waveform capture. So with the simulated waveforms, you follow the steps, like select what test you want to run, configure the test, and then run the test. And at the end of the test run, you get a report. A high-level report will list if it's a pass or a fail. A more detailed summary will give you what test has been run, whether it's a pass or a fail. Let's say if there's a failure, you can further look at the waveform from which the measurement was extracted. So that's the overall flow. In other words, you run the simulation, generate the waveform, save the waveform to a file, run the compliance test, then get a report. And if needed, if there are failures, you can debug the failures. So here is what the compliance test bench organization looks like. So on the right-hand side, you see this dialog box. And so the way the compliance test bench is organized is it has a set of cable and a test fixture models. It has termination models. It has reference models for the host, for the cable, and for the device side. And it has a list of channel simulation examples with generic models or with the USB 3.1 reference models available from USB implementation forum website. There are also S-parameter simulation examples, again with some generic models or with the USB implementation forum reference models. And for these setups and models, there is a documentation. So that's the compliance test bench organization in ADS software. As I pointed out earlier, you can substitute some of the simulation models with your actual measurement data to debug the hardware prototype. And after you run the simulation, the waveforms will be saved, and then you use the Infinium Offline compliance application tool to post-process the simulation waveform and get the compliance report. So here is a summary of the simulation models. So for the host and the device transceiver models, I'll talk about how to get those models. For the host PCB models, we have the minimum loss models and the maximum loss models. They are all S12P files. You may ask why it's a 12-port touchstone file. Basically, for the D plus D minus differential pair, that's a 4-port. For the transmitter to receiver link, going from the host to the device, that's another 4-port. Then from the device to host, that's another differential pair, that's another 4-port. So put them together, it's a 12-port touchstone file. For the cable and the connector models, there are also a set of different combinations, like standard A connector, standard B connector, micro B connector. There are different combinations of S-parameter files available. I'll say a few words about the transceiver models. So the host side has a transceiver and the device side has a transceiver. And there is a behavioral modeling tool we have called System View. So this is a high-level diagram of the System View transceiver modeling. So the box in the left-hand side basically is a pattern generator going through some waveform shaping function, then going through the transmitter function. Basically, it is a 3-tap FIR or finite impulse response filter. Then the block in the middle is an S-parameter file or S21 data, and the block on the right-hand side, that is a receiver function. Inside the receiver, there are several functions available. There's a CTLE function, the clock data recovery function. The clock data recovery is further decomposed into some smaller blocks, such as frequency frequency phase detector and the VCO, those type of more fundamental elements for a CDR. And then there's a decision feedback equalizer inside as well. So the top level, those CDR, DFE, and CTLE are listed as parameters below the block. And the iProbe is inserted in several points to indicate what the eye looks like at that particular point. For example, before the signal goes into the receiver, the eye is closed. Then after CTLE and the DFE, the eye is open. So you can use this kind of behavioral modeling approach to look at the transceivers for a host or for a device. And let's say if you are designing transceiver IP, you can use this type of method to model your transceiver IP or match the behavior of your transceiver IP. And after you are satisfied with the behavior of the transceiver behavior, then you can do a IBIS-AMI model generation. So System View has the capability of generating C++ code from a high-level diagram. So this is a kind of a illustration of how this works. So for the transmitter, you highlight the block and say, I want to generate C++ code for this. For the receiver, you can say, I want to generate a C++ code for this as well. And then every function or every lower level model inside the transmitter or the receiver will be generated in C++ code. Then there is a utility to compile the C++ code into either a DLL for the Windows machine or a .so file for a Linux machine. Then those DLL or SO files can be used in running IBIS-AMI simulations. So this is a code generation tool available in a piece of software called System View. Once the AMI models are generated, they can be referenced in a channel simulation tool such as ADS. So this slide is showing a TX-AMI model referencing the IBIS-AMI model I just generated. The name is ESOF_USB3_TX. And the block on the right-hand side is a receiver AMI file, a model referencing the ESOF_USB3 RX IBIS file. And the TX AMI and RX AMI have a set of parameters the users can set. For example, for the RX AMI model, you can set the CTLE parameters like ADC, 0 location, the 2 pole locations for Gen 1. For Gen 2, you have the DC gain, AC gain, pole locations, FP1, FP2. The DFE parameters can be set as well. The CDR parameters, for example, the VCO sensitivity, the loop filter parameters, all of those things are settable by the user. And you can do a simple test by directly hooking up a RX AMI model with a TX AMI model and look at the eye diagram. Of course, in such an ideal situation, the eye is ideal, wide open. So that's a way to test an IBIS-AMI model in a channel simulator. Of course, these are the kind of like reference models you can use. If you buy a transceiver or transceiver IP from another vendor, typically the vendor will give you some IBIS-AMI models. So with the AMI models, you can set up a overall link level simulation by connecting the transmitter to the package PCB via transitions and the connector and the cable models. Then on the receive side, you connect the receiver to the package and PCB models. And you run a bit-by-bit channel simulation, and you can observe the eye at different locations along the channel. And at some points that, for example, closer to the transmitter, the eyes will be open. Then after the signal propagates through the channel, typically the eye is closed. Then the receiver side equalizers will open the eye. And so you can do the eye measurements and superpose the mask with the eye and see if there's any overlapping between the mask and the actual eye. And again, this is another diagram showing how the overall compliance test is done. So that is, you set up the simulation, you run the bit-by-bit level channel simulation, you save the waveform, and then the saved waveforms, which are in the format of HDF5 file, is a binary file format that is pretty compact. And the Keysight Infinium software is able to read that file and use that file to run a compliance test. Then at the end, you get a compliance test report indicating pass or fail. And if there are failures, there are tools to help you debug the failures. So now, in the previous slides, I talked about the bit-by-bit channel simulation and running compliance test. In many cases, running S-parameter simulations is also very helpful. So this is a setup for running an S-parameter simulation. Again, you can do this individually for a connector, for a cable, or for a PCB trace. You can also cascade many different pieces of the channel into an overall end-to-end channel and run as parameters. And you can do the usual S parameter measurements such as insertion loss, return loss, the far end crosstalk, the near end crosstalk, overlap those simulation results with the masks. You can also derive the channel metrics such as the insertion loss, fit at the Nyquist frequency, etc. So this is also a very typical type of simulation you run individually on channel elements or run overall end-to-end channel. Another common or useful simulation setup is a TDR or time domain reflectometry simulation. Again, this is TDR is accomplished by launching a step into the channel and observe the reflected waveform. And this kind of simulation can review very intuitively what the impedance profile looks like. For example, the two traces I put in this plot, the red trace is the impedance profile looking from the left to the right, and the blue trace is the impedance profile looking the other way from the right to the left. So this kind of impedance profiles are very intuitive. It gives you an idea of where the signal reflections are happening, and that sometimes help a designer to debug a particular part of the channel when there are compliance violations. That pretty much brings me to the end of the webcast. So here is a summary of what I talked about. USB 3.1 Gen 2, also referred to as SuperSpeed Plus. The physical layer is running at a pretty high speed, 10 gigabits per second. That is well into the so-called microwave frequencies. And to put it into layman's term, with this kind of speed, you can transfer a high-definition movie, a full-featured movie, from, let's say, a thumb drive to a computer in less than 1 minute. And for a channel, typical channel, after the signal goes through the host channel and the cable connectors and the cables, the eyes are typically closed, and so both the transmitter equalization or conditioning and the receiver side signal conditioning are needed to reopen the eye before the receiver can make a decision on whether the bit received is a 1 or a 0. For those of you who are familiar with a hardware test, in this webcast I am pointing out that even before hardware prototypes become available, you can run simulations and save waveforms and run compliance test with the simulated waveforms. And you can play with numerous channel conditions and equalization settings in simulation, and see how you can make the design more robust before you commit to hardware. So I'll stop here, and overall, Keysight has the simulation tools and measurement tools, as well as the expertise to help you conquer many of the challenges in getting a USB 3.1 physical layer design to work. So with that, I'll hand this back to Don.
Thank you. All right, a few of you have already submitted questions, and we'll jump right in. If you'd like to submit a question now, you can type it into the question window on the side of your screen and hit submit. Now, while we're answering your questions, we'd like you to complete the feedback form that's located at the top of your console. You can also access that survey through the red globe on your widget bar. So jumping right in, did the device repeater sublinks require dedicated simulations? That is, in a full channel simulation, do the repeaters get their own IBIS-AMI model?
Okay, so if you have a very long channel, and let's say if the channel, typically if the channel is has more than 23 dB loss, you will need a repeater. And a repeater, fundamentally, it is either let's say a retimer, for example. Yes, indeed. In simulation, you will need a repeater model, and repeater can be a back-to-back kind of back transmitter and a receiver, and you can reference a transmitter IBIS-AMI file, and then reference a receiver IBIS-AMI file in the same retimer model.
All right, from the same viewer, what's the channel used in a standalone compliance application? Is it a measured S parameter or a USB standard compliance channel?
In the simulations we run, we used the reference channel models available from the USB Implementation Forum website. We also built some typical channels with the ADS built-in transmission lines, via models, and S parameters from other sources. And in a real application, you would need to substitute many of those models with your models because each design is different.
All right, another questioner then. Can ADS channel sims be run in statistical mode given 12B/13B encoding scheme for USB, that scheme used for USB 3.1?
Let me make sure I answer this accurately. So yes, ADS channel simulation has two modes. One is bit-by-bit mode. The other one is statistical mode. And so there are a couple of encoding schemes available. Those encoding schemes are applicable in both bit-by-bit and in statistical mode. So I know there's 8B, 10B mode. There's 120B, 130B. There's 130B, 132-bit mode. So yes, in summary, yes, I think the encoding schemes can be used in both the bit-by-bit mode and in statistical mode.
Thank you. Can you talk a little bit about sophisticated calibration?
I was mostly referring to the receiver compliance test. That's where I use the word sophistication, because well, in a receiver compliance test, you need an instrument, let's say a jaybird, to generate a pattern, test pattern, and then each type of jitter can be controlled rigorously. Then that pattern will propagate through a reference channel and some test fixtures. And then on the other end, before you hook up your DUT, you need to hook up an oscilloscope to calibrate the level, the signal level, and the eye opening, the eye width and eye height at a particular BR value. So that calibration process is very critical before you do the actual BR test or loopback test. Because once the loopback test starts, you are basically sweeping a set of values of SJ amplitude and frequency, and you get one error, it's a pass, or zero error is a pass. You get two errors, it's a fail. If the calibration is not done carefully, you may get false failures. So that's what I refer to. If you want to know more about the calibration procedure, there was a webcast on that topic on March 11th, 2015 by my colleague Torsten, and he has a lot more details on how the calibration is done.
Okay, let's talk about the receive test and cable length. I think you showed a 6-inch cable length, and the listener's under the impression that it should be a meter in length.
I'm drawing from a blank right now. Sorry, maybe I'll answer that question offline.
Okay. How about this? How about this? Is there any place you can find a design guide for 3.1?
A design guide for a 3.1. The ADS compliance test bench is kind of like packaged in a design guide format, and hopefully that kind of design guide is useful in designing the host side or the device side elements. There are many documents published on USB 3.1. Those documents are available. For example, like there is a equalizer design guide. That's for 3.0. 3.1 equalizer design guide I don't think is available yet. But anyway, in short, I hope the compliance test bench in ADS is sort of a useful design guide for a user.
All right, where can someone get the oscilloscope software for laptops that you talked about in slide 27?
I believe you can download the Infinium offline software and the compliance application software from Keysight.com. So let's say if you go to Google, you search for a particular application, you download that and you can install it on your PC. Today, the Infinium software and the compliance application software packages can either be run inside a scope or run on a standalone PC, and they are downloadable from the Keysight website.
Okay, I think that's the same answer to the next question, which is about the compliance test bench.
The compliance test bench is a kind of like it's an add-on to ADS or Advanced Design System software. It is available. Actually, it will be posted on the Keysight website on April 6th, I believe. So it's not available yet. If you need it today, you have to contact one of us. We'll give you access, but it will be publicly available on April the 6th, 2015.
Okay, well, we've run up against the top of the hour, And so that concludes today's presentation. On behalf of Electronic Design, thank you for joining the webcast today. Now, you are invited to attend our next event in the Tutorials and Signal Integrity webcast series. That one's called Extraction, Verification, and Usage of Short-Haul Opto VCSL Models. That'll be on May 28th. Thank you to Keysight Technologies for sponsoring this event today. And to everyone out there, have a productive remainder of your day.